Good evening, Dr. Murphy, Mrs. Bierman, members of the Board of Education, and the greater Ramsey community. Tonight we will be delivering an update on science education, and specifically what it looks like at Dater School. To get you in the right frame of mind, we will start by looking at a phenomena captured on video. I'm not sure if you've ever watched a bouncing golf ball before, but you will tonight. As you watch, there's two questions that I'd like you to think about as you watch the event. The first one is, what do you notice or what do you observe about the event? The second is, what questions or wonderings do you have? Now, I know that was kind of fast, so we'll watch it one more time. Again, what do you notice about the movement of the golf ball? If we were in the classroom, we would give you a few more minutes to process your thoughts. But you just observed the phenomena, which is any observable event. It could be captured on a video, a data set, a graph, a picture. The inclusion of phenomena has become an important element of instruction to engage students of all ages in building a mindset to figure it out. Today's science standards involve three pillars or dimensions that are aimed to support student sense-making. The first dimension are the disciplinary core ideas. These are a limited number of core ideas in science and engineering. These choices were made to avoid shallow coverage of a large number of topics and to allow more time for teachers and students to explore each idea in greater depth. Each idea increases in sophistication as students progress across the grades. The second dimension are the science and engineering practices. These 8 practices represent what students are expected to do. They do not operate in isolation. Rather, they tend to unfold sequentially and even overlap. For example, the practice of asking questions may lead to the practice of modeling or planning and carrying out an investigation, which in turn may lead to analyzing and interpreting data. The last dimension are the cross-cutting concepts. The 7 concepts are used across the different science disciplines, and their purpose is to help students deepen their understanding of the DCIs. While the ideas of patterns, cause and effect, and structure and function are not new, what is different is the call to use explicit instructional supports to build flexible thinking with the cross-cutting concepts. The integration of these 3 dimensions is called three-dimensional learning, and 3D learning shifts the focus of the science classroom to be a place where students gain confidence to flexibly use core ideas and the cross-cutting concepts with the science and engineering practices to learn. Lessons are designed to give students experiences first, followed by discourse and crafting explanations based on evidence. Tonight we will showcase how an interactive science notebook is being leveraged to address three-dimensional learning and to build student capacity to use the practices. We will look closely at the practice of developing and using models and analyzing and interpreting data. Lastly, we will share an update about the STEM enrichment opportunities at Dater in light of the COVID restrictions.
Hi, I'm Mrs. Davidson.
Hi, I'm Sophia.
And we're going to talk to you about
interactive notebooks. An interactive notebook is a tool we use to make our thinking visible. It is a space where we can revise our thinking in light of new evidence or new learning. The notebook is said to be interactive because it requires us to make it. It is highly structured with a table of contents, expectations, and it clearly tells us what is considered input. The teachers create that, and output, what we create. We have all used a digital form of the interactive science notebook during the pandemic.
Dater Science has optimized the use of the notebook to engage students with phenomenon at the start of every unit. An I See, I Wonder chart is used to capture student noticing and observations along with providing an opportunity for students to engage in the science and engineering practice of asking questions. Lessons in the unit are purposefully sequenced and designed to support students in garnering knowledge and evidence to offer an explanation for the phenomenon at the conclusion of the unit. Notice the circle in the upper right-hand corner of this slide. This denotes to the students that they need to contribute their ideas to the slide. Shared with the students at the beginning of the unit of study are the disciplinary core ideas, or big ideas about the topic. These are not meant to be hidden from the students. They are made available to students to use to help explain observations, evidence, or ideas. Notice the triangle in the upper right corner of the slide. This is considered input provided by the teacher. As the notebook went digital, Google slide decks were strategically created. Student output slides provide a specific location for a student to communicate their thinking via text, photos, or video clips. When possible, students carry out safe and simple investigations and modeling tasks at home using materials provided by the teacher or found in their home. Students can then insert pictures or videos of their work into the notebook. Student work posted to the notebook shows continued growth in the science and engineering practice of obtaining, evaluating, and communicating information, as well as the profile of a graduate competencies of adaptability and self-direction. Students have grown by leaps and bounds with using features of Google and Schoology while contributing to their notebook. COVID safety protocols have limited the hands-on experiences in science, and alternative digital tools or teacher demonstrations have been used to provide students with data to analyze and interpret. Teachers have leveraged video to introduce activities and record experiments for students to view and capture data. Integrating this instruction has been essential in continuing to facilitate growth in the science and engineering practices, as well as to provide authentic context for students to apply the cross-cutting concepts and big ideas. At the end of a learning cycle, students are presented with a question in which they need to construct a scientific explanation using a claim, evidence, reasoning framework. Crafting an explanation using data as evidence along with the facts and scientific principles as reasoning is an important aspect of students transferring their learning to a novel context. It provides students with practice in flexibility using the big ideas and effectively using data as evidence to support claims. At the end of the unit of study, students return to the opening phenomenon to see if they can now make sense of the event using the big ideas from the unit, data from unit investigations, and acquired knowledge. A student can look back to their first thoughts and see how they changed over the course of the unit. The notebook provides information on learning to both the student and teacher because student thinking was made visible on a consistent basis.
Hi, I'm Miss Calendrillo.
And I'm Kate.
We're going to talk to you about
Developing and using models.
Do you remember building any models for science when you were in school? The practice of developing and using models goes beyond just the production of a physical model. Today, scientific models include diagrams, physical replicas, mathematical representations, analogies, and computer simulations. The models are used to represent a system under study, to aid in the development of questions and explanations, to generate data that can be used to make predictions and to communicate ideas to others.
In grades 3 through 5, we are expected to use a model to test cause and effect relationships or the interactions of the parts of the system. In this example, when we revise our models, we can communicate the predicted outcome and how a change in the forces in the game of tug-of-war can show unbalanced forces. Models can also be used to help us acquire knowledge and make meaning of the bigger concept. When we construct the model while we are thinking on how to mimic a natural process, we are able to understand the underlying science which is driving the result. In this case, we were learning about the movement of Earth's tectonic plates to produce a desired mountain type.
Computer simulations are another type of model available to students today. Simulations allow students to easily manipulate system components to produce different outcomes. Students can test different predictions, and multiple trials can be attempted to create data sets. In their study of energy and energy transformations, students explored electrical circuits. Both the computer simulation and manipulatives allowed students to develop digital and paper-based circuit models. The modeling task also prompted students to ask questions. If you notice on the paper model, the student is wondering how fast the electricity is traveling through the circuit, and they are wondering how the paperclip is able to conduct electricity. An unfortunate consequence of COVID right now is a limitation on student collaboration. Where possible, data science has transitioned what would have been collaborative performance tasks to independent tasks. In this case, students are using paper models to predict Pangea. Even at a young age, it doesn't escape our students' attention that some of the continents look as if they fit together like the pieces of a puzzle. Students also explore and use the fossil and rock data found on the present-day continents as further evidence for Pangea. Whether models are paper, digital, or physical doesn't matter as much as how our students are using the model to predict, test, explain, and communicate ideas.
Hi, I'm Mrs. Gesualdo. I'm Miss Thompson.
I'm Nicholas.
I'm Brady.
And we're going to talk to you about
Data Talks.
The practice of analyzing and interpreting data has application beyond the science classroom. It is increasingly important to build student confidence and capacity to interpret different data visualizations to develop their data literacy. Data organized into tables and displays can reveal patterns that indicate relationships. This analysis and interpretation can provide evidence for scientific explanations and help students in making sense of phenomena.
In a data talk, we are shown a data visualization, a graph, data table, or infographic. We have to think about the questions. What do you notice? What do you wonder? The activity gives us the time and space to practice interpreting a variety of data and data representations. It also gives our teacher the opportunity to teach us how to read the title, axis labels, and key, along with asking, what is the source of this data?
When I first see the graph, I immediately look at the title to learn what the graph is about. Next, I examine the axis to see what the variables are. I also know to look for a key that will provide more information about the data. I have enjoyed participating in the data talks this year because it's interesting to hear what my classmates notice and whether it is the same as me. I also like being able to ask questions about the information and to think about what it may mean.
Students have grown in using data talks in a short period of time. Their level of comfort and confidence has increased, and they are not intimidated by the changing nature of the graphics. They've also increased their self-awareness, and they are able to analyze the visuals so that they can really notice the smaller details, which helps them to generate more sophisticated meaning. They've also seen a greater connection between math and science through the visuals.
In addition to all of the science learning that goes on in our classes every single day, Data is also the place in a child's K-12 continuum where we start to offer extracurricular activities. This year we have a couple of really cool new science-based activities that we're offering. They're both up and running and doing very, very well. So you're going to hear about our Lego Engineering Club and our STEM WOW Fair coming up.
The Data Lego Engineering Club gives students a chance to have fun while practicing science concepts. I love Legos and I love to build cars. Mr. Quinlan helps the students learn science during the Lego Engineering Club.
In this club, there's an emphasis on creativity and problem solving using your own Lego sets. Now, what properties of physics are we going to learn in this club? The first task we have this year is to build a Lego balloon-powered car. It might not seem like it at first, but a simple balloon car is loaded with physics and engineering concepts. Another way to think about the balloon's movement is to use Newton's third law of motion. For every action, there is an equal and opposite reaction.
Hi, I'm Mrs. Corey, the enrichment teacher, and I'm going to talk to you about the STEM WOW Fair. This year, Dater School is hosting its first virtual STEM fair. This event will integrate areas of science, technology, engineering, and math, and provide students the opportunity to use either the scientific method or the engineering design process to conduct research and solve problems. This year, 36 Dater students will participate in our STEM WOW virtual fair. 13 students have chosen the engineering design process, and 23 have chosen the scientific method to guide their explorations. Each student will receive his or her own web page to submit all of their collected information. Students are encouraged to use pictures and/or video. These web pages will be published on the enrichment page of the Dater School website during the week of April 12th through the 16th.
Hi, I'm Riley. My STEM WOW project is about speed and velocity. In my project, I plan to find out if the speed and velocity of an object change depending on its weight. While I'm not done yet, so far I have learned that the weight of an object doesn't affect its speed, but it does affect the amount of energy, kinetic energy to be specific, an object has stored.
As you can see, at Dater School, all of our science instruction and our extracurricular activities are designed to engage our students, support our standards, and promote the Ramsey Profile of a Graduate. We thank you for your attention tonight, and thank you for supporting Dater School. Thanks to Sophia, Kate, Brady, Nicholas, Riley, Nishant, Mrs. Davidson, Mrs. Calendrillo, Ms. Thompson, Mrs. Gesualdo, Mr. Quinlan, and Mrs. Corey for their work in this presentation.